And
Once. I'm Derek Grove from the University of Kansas, physicist at CMS.
Hey, Andres. I'm originally from Puerto Rico. I work with the University of Tennessee in Knoxville.
and hi, I'm Claire. I'm also a physicist. I was born in South Africa, and right now I'm working for a Hungarian institute. So representing from all around the world here today. It is amazing to have you guys with us. Why don't you drop a just like write down in the chat on YouTube where you guys are from, so we know where you guys all are in the world. That would be great to see. Yeah, so welcome to the absolute best experiment in the world. We are going to take you on a tour almost 100 meters underground, and Derek is going to be our underground guide today.
For sure. So if you don't know where we are, let's just say this is in Cessy, France. It's near Geneva, Switzerland. But we are at the compact muon solenoid experiment. And we've been doing this experiment for quite a while now. But we are doing fundamental physics, also known as particle physics here. We collide these protons at very high energies, and we see what they do afterwards, what other particles are created, what they decay to, things like this.
Maybe I should say this is going to be a really cool visit. We're just closing up the machine and we're getting ready for collisions this year. So we typically have a period of several weeks at the end of the year where we do maintenance and do any kind of upgrades we need. So it's a great time to visit. The magnet is running, so we're going to be showing you guys the effects of the magnetic field. And we'll talk about that, a lot of this along the way.
Yeah, so the goal for this visit is for you guys to get to answer or to ask us whatever questions you have about particle physics or the type of thing that we study here at CERN, or what is going on behind us in the control room. Anything that you see on the screen, anything that you would like to know, please ask us. You can type in the chat in Google, in YouTube, sorry. Yeah, so without further ado, shall we head on down?
Yeah, I need to get going.
All right, so get your helmet and safety shoes. Yeah, and Andres and I are going to stay up here in the control room and chat to you. So yeah, let's see. What do we?
Well, I mean, we can start by describing the LHC, I think, and I see there's a question about how large the LHC is. So you can maybe start us off with that.
All right, so the LHC is the world's biggest particle accelerator. It is 27 kilometers in circumference, and it is buried about 100 meters underground. And in that 27-kilometer long tunnel, we have more than 9,000 magnets all lined up, and those magnets' job is to keep the protons going around in a circle and staying nicely packed together, so that when we point the two beams at each other, they collide and we get all sorts of interesting things happening.
Yeah. So yeah, this is all happening in the Geneva area, as we said, but we're pretty far away from the city of Geneva and also from the CERN main site. So it's about a 20-minute drive from the main site of CERN. And as you may already know, we have multiple other experiments around the LHC ring. So we're going to be discussing mostly CMS, but if you're curious about the other experiments, we can also talk a bit about that. And we hope to talk to you about CMS, what's going on this year, but also what's coming up on the horizon. So we're looking towards a major upgrade of both the LHC and most of the LHC experiments. So we hope to also tell you a bit about that. So I see that Derek is now about to enter the elevator area. Maybe we can check with him real quick.
Yes, so at CMS and CERN alike, we have many different safety procedures. And so when you're entering one of these restricted areas, you must have your own personal dosimeter. So this has my name on it, but it's also linked to the biometrics of my body, like my retina. So what's going to happen is I'm going to scan this. It's going to know that it's Derek trying to enter, and then it's going to shut me in this room, scan my eyeball, and if my eyeball matches this ID or what's on record, it will let me through. And this is how we access the underground and the other restricted areas at CMS. So let's see if it works.
Access,
now,
oh, sorry.
Nope, I'm just saying it scanned my eyes and we're all good.
There
And now
we go.
Naomi will do the same.
Naomi's behind the camera, so we won't. So
Yes.
she's the camera person here, going with Derek underground. We may lose signal with them for a little bit as they go down in the elevator.
Right now, too.
All good. So yes, while we're going underground, we'll keep the camera on, but you guys can continue to take questions or answer the questions or say whatever you like.
Oh, look,
And the
they see the
magnet's on.
light there that shows the magnets on, exactly. Yeah, so as you can see, we take safety very, very seriously at CERN. All the restrictions are when entering places. So it basically is impossible to get into a place that you do not have the correct access rights for. And those access rights are based on whether you have been properly trained to access those places.
Since maybe to give a bit of introduction, maybe we can discuss a little bit of what CMS is and what it's like. So we often say that CMS is a bit like a cylindrical onion. We just mean that in the sense that it has many layers inside of layers inside of layers, and it's made up as a cylinder. Yeah, we can show you a picture of what CMS looks like a little bit if you took a bite out of it, and you can see the inner layers and these inner detectors we use to reconstruct the trajectory of particles. Then we have additional layers that tell us about the energy of these particles. And in CMS, then we have a very large magnet. We have a superconducting solenoid. It's a very strong magnet. You can consider it an electromagnet that we cool down to extremely cold cryogenic temperatures, and it produces a very strong magnetic field. So we use that to bend the trajectory of the particles, and that tells us about their momentum. With the combination of those detectors and then all of the muon systems outside of CMS, we try to capture a full picture of what happens in the aftermath of these collisions. And so there's a lot of detective work, if you will, to try to understand what's going on in these interactions. I don't know if you want to add. This is as quickly as I can.
Right. No, it's kind of like, being a forensic detective. Imagine that you've come across a car accident. You've had two cars collide head on, and bits and pieces of car have flown outwards from that collision point. Your job would be to go and collect up all of those pieces and then use them to rebuild what had happened, to allow you to reconstruct what happened at that collision, and that would tell you about exactly what happened at the collision. And that's basically what we're doing. Instead of bits of car, we are just collecting particles. So when you have two protons that collide head on inside the Large Hadron Collider, those protons can fuse together and turn into different kinds of particles, like, for example, the Higgs boson. And then that Higgs boson will disintegrate and send bits and send other smaller particles flying outwards through our detector. So our detector catches all of those particles, and we, the physicists, put all of that back together and tell you, oh, this event looks like it created a Higgs boson, or maybe something more exciting.
So since we're on the topic, I can maybe answer a question quite quickly. So there's a question about how strong the CMS magnet is. Claire already mentioned there's thousands of magnets around the OHC, so we're specifically talking about the magnet in CMS. And our magnet, as I said, is a large magnet, 6 meters in inner diameter, is about 10 meters long. And we circulate 18,000 amperes of current. So a lot of current going through the magnet to generate 3.8 Tesla. And this is comparable to an MRI machine, for example. So it's some of the strongest magnetic fields that humans can generate, or comparable to the strongest magnetic fields humans can generate. And in particular, it's unique because it stores the most amount of energy of any magnet in the world for now. So when the ITER experiment is completed and operational, it will store a larger amount of power in the magnet, but for now, it's the CMS detector. So perhaps we can switch to Derek, I think. Oh, not quite yet. So they're still getting ready. We can maybe...
Oh, This is an interesting question from somebody called Multi United on TikTok. Do we need specific cameras while filming near the detector underground?
So we will kind of see just momentarily because our colleagues are now entering the cavern, but you will see that sometimes there's an effect of the magnetic field on the cameras, and typically this is the focusing on the camera, but this also has an effect on the stabilizing gimbal that we use. And maybe Derek can tell you a bit more about that, but I think we can just switch. Yeah, Derek.
Am I live? Okay, so we're in the experimental cavern now, and this is the compact muon solenoid. This is the detector right behind me. So this really gives you, I hope, a sense of scale for how big it is. And maybe I'll go closer to it so you can compare a grown man, I think I'm fully grown, to the size of this thing. But it's quite
15
large.
meters tall. Yeah, it's 15 meters tall in diameter. Yeah.
And so this thing is a massive industrial scientific experiment that we're doing. And that's partly why we need such large facilities and so many physicists and engineers and software engineers and safety people, all these different people working on it, because this is the scale of the science that we're doing now. And yeah, to get back to that question about the camera, we had to take a moment there to switch our gimbal to a manual. It's just a stick now, because if we bring that in here, the magnetic field from this detector behind me, to show you there's a strong field here. Maybe you can see this curling a bit. This magnetic field would affect the gimbal and our camera wouldn't stay steady. So we have to switch how we're holding the camera. And then also throughout this visit, if our camera feed kind of does some weird, I don't know, out of focus stuff, that's also sometimes from the field affecting the autofocus of the camera. So I'm holding some magnetic objects here. If you can see, there's quite an effect, even standing this far away from the detector. But now we're going to move closer and we're going to see what happens, because the magnetic field is weaker the further you are from the source. But then, of course, if we get closer, we're going to see more and more of this crazy field.
And the magnet is right inside the center of the detector there. Well, it's about a 6-meter diameter tube, basically, cylinder that's inside the detector above Derek's head. So we're not even touching the magnet right now.
Yeah, you have to consider that the magnet is quite a bit. So the magnetic field inside the magnet is 3.8 Tesla. That's an extremely strong magnetic field. And then outside of the magnet, we can produce up to 2 Tesla. But in the regions where Derek is, the magnetic field is significantly smaller, but still incredibly noticeable. As you can tell, it's very remarkable. And maybe just one more thing. So we actually just ramped up the magnet to the full field yesterday. So again, we're in the process of preparing the detector for collisions in the next couple of weeks.
That's awesome.
Derek, do you wanna describe a little bit what this experience is like?
So, I mean, it is hard to describe, but I'll do my best. It is quite magical. That's a great word for it. Although it's not magic, it's just physics. It's strange holding something and you can feel that, you know, there is this invisible thing kind of tugging on it and wanting to take it over there. And so this chain that I'm holding, it almost looks like it's some snake or something, right? That's like being charmed, but really it's just being aligned with the field from the solenoid. And if I'll go ahead and let it touch. So this red part here is a big, I believe it's steel, right? It's a steel support for our detector. And so steel is, of course, magnetic. So you get all this interesting effects where you have the original field from the solenoid, but since steel is a magnetic material itself, it will have this induced magnetic field. So all to say, there's magnetic fields all over the place, and anything that is magnetic, like this chain or the steel, you're going to want to align with this field and kind of play with it a bit. So
it's maybe worth remarking that we have a lot of steel in our detector. So I mentioned before that inside the magnet, we have the strongest magnetic field, 3.8 Tesla. And around it, we can generate up to 2 Tesla. And that's because we have a lot of steel around the magnet. We can sort of redirect the magnetic field lines to reinforce the magnetic field. And that means that we have about 12,500 tons of steel in our detector. That's something like twice as heavy as the Eiffel Tower. So it's really quite a heavy detector because of all the steel that we use.
Derek is demonstrating a very, very important point here, and that is when you are bringing tools in to the cavern, you have to be very careful if you are using tools that are magnetic. So I've actually been in the cavern while the magnet's been on, and I had to go to replace a power supply. And just walking past the detector, holding a screwdriver, which kept trying to turn in my hand to align itself with the magnetic field. It was a really weird experience, you know, because it's this inanimate object that's like trying to move on its own.
Yeah, and it gets really crazy when you're carrying something really heavy. So I've had to carry power supplies that are extremely heavy, and then trying to put them where you want while the magnetic field is on. It really resists you, you know.
That's awesome.
Yeah, and so maybe I can just quickly also describe, you know, this is one continuous piece of metal that's magnetic. And so the whole thing wants to align with the field. And so I can kind of feel this alignment. You know, if I try to twist it, it doesn't want to go in either direction. And this is a pretty freaky thing to feel. But if I turn it far enough, it will flip over, kind of snap into the other orientation. But it really wants to be in either direction where it's parallel or aligned with the field.
What about you, Derek? There's a question on YouTube by Yamna Shaikh 8210, who wants to know if the magnetic field is affecting human bodies.
So it's a very good question. What I can tell you from my experience is I don't feel anything, not in my body, my head, you know, any part of me, my fingers. I don't feel any sensation like this, these magnetic materials do. But, you know, it's an interesting thing. Water is slightly diamagnetic. I believe that's, if I remember from my physics class, that's what it is, which means no matter what your magnetic field is, water can be slightly repelled by it. Even so, this is a very strong field, and I'm mostly water, but the effect is negligible. I still don't feel anything from this field. And magnetic fields, when they're static, meaning when they don't change, if it's just this constant field, my opinion as a physicist, doctors may have others, my opinion is that they're pretty safe because the field isn't changing. I don't feel any effects. Now, certain medical equipment uses strong magnetic fields, and sometimes the magnetic field changes direction rapidly, and then that can start to affect the body, or at least measure things about your body. But none of that happens here at CMS. We have a strong field. It doesn't change. I don't feel anything.
Yeah, so maybe just to add to that, one thing that is important for colleagues and visitors is that if anybody has any kind of magnetically susceptible magnetic implant, right, such as a pacemaker, then there's restrictions, there are legal restrictions to this. And yeah, I'm not an expert on these things, but apparently for there to be any effect on organic tissue, I think the magnetic fields need to be significantly higher.
At least 100 times.
At least 100 times. Yeah.
So Derek's taking us for a nice walk now down. He's at the bottom, like underneath the detector, basically, and he's walked from one end of it across to the other.
Yeah, and maybe, I don't know if you were able to tell that the direction of the magnetic field lines also changes.
Yes.
It does that. So the direction in which the materials he's holding are pointing to is changing as he walks around the cavern.
Yeah, because this was pointing towards the center of the detector on the other side, and now it's pointing away, right?
Yeah.
That's cool. It's very cool.
Well, to be completely honest, the chain sometimes is not the best assistant for demonstrating because it can do these weird things where it folds in half. It's very cool, but yeah, as you noticed, when we walked underneath the detector to the other side, the chain did swing, and that's because our field changes directions as we move around our detector. So
cool.
we can maybe go up and show a view from above. We're all the way on the ground floor, but why don't we climb these stairs?
Derek, while you're there, let's
Yep.
take a, there's a lot of different colors in the structures there. And
Oh, yeah.
Sun 786 wants to know if the different colors have specific meaning.
Well, honestly, to me, I like all the colors because it's a beautiful, amalgamation. It's better than having just one color, right? But personally, I don't actually know if the colors have any significance. I can point out what the different things are. So this red part is the steel. What do we call it? Do we call it the end cap? But not the end cap, but it covers the muons, right?
The muon
muon
end plate.
detectors.
Yeah.
Muon
Steel
end
is
plates.
always red.
Yeah,
Yeah.
steel is
Yes.
always red, and that's, I think, an aesthetic choice that somebody made. I don't know who.
Yeah. Green
But
is
then what about-
structural. Green is
Yep.
like structure, which I think is structure built by CERN, whereas like the blues is like structure built by the experiment, like us, ourselves.
Yeah, so this yellow structure, I don't know the origin of why it's yellow, but this is the support for the hadronic forward calorimeter. And then we have just on top of Derek, there's a very large orange block, and this corresponds to the. Actually, you mostly can see the new forward shielding, but there's even more shielding inside of the orange shielding you see on the right here. And so I think also Noemi is trying to show that you can see the main shaft just above. And so this is, again, it's a hole that through which our detector was lowered down. And our detector is designed in slices. It's a modular detector. So I mentioned the cylindrical onion. It's actually segmented into about a dozen slices. And each of these was assembled on the surface, tested on the surface, and then lowered down by dedicated cranes one at a time.
Yeah, so
We
that
can show
hole is
you-
it's like a hole, it's a tube that goes up to the surface.
Exactly.
We can
there's
show you
also-
some of these slices
yeah,
Hmm.
so
real quick.
So yeah, you can actually see these gaps. Maybe Derek, you can point them out a bit more clearly.
Yeah. So this gap here,
Yeah, you can see the light coming through. So that's a really segment. So this separates these slices, and you can see the size of them. Now it may not look like they're very large, but each of these slices is extremely heavy. So even the most lightweight slice is on the order of 300 tons. And the center slice, it contains the magnet, and that's about 2,000 tons in weight. And also, since we're here, you can see there's a lot of cabling, and you can see there's also colors here. So there's blue, there's reds. So pretty much universally, the red cables correspond to high voltage cables, and exactly, and other cables could be low voltage. There's fiber optics, so there's also some color coding there.
I'm going to leave my magnetic things here because as they're in my pockets and I walk around, I feel them moving. And so I would rather not have that.
Awesome.
We will return down here and play with the field some more in just a moment. But first we want to go and just give you this top down view from all the way at the top. And again,
Don't
help you
let them
see,
in.
help you see the size of this thing.
That's great. Thanks, Derek. Don't forget to pick them up when you come out
Oh,
of
of
there.
course.
We don't want to leave them.
Actually, I will bring one.
to remind you.
Yes.
So Mustafa on YouTube was asking if we use other materials as well. So I mean, there's a lot of steel in here as a support structure, but also because we are specifically using it for the purpose of helping create this magnetic field, which allows us to bend the particles as they come out of the collision points. But different parts of the detector are made up of different things. For example, the very, very center of the detector is all made out of silicon. And then we have,
And well, maybe I can also add to that. I mean, in the innermost parts of the detector, you design it in such a way that you don't interfere with the trajectory of the particles, because that's what you're trying to measure. So you have silicon, which is a more lightweight material. These sensors are similar to camera sensors, but the support structures are carbon fiber. Again, you want to avoid interfering with the trajectory of the particles. Whereas other detectors, you want to do the opposite. You want to stop these particles, right? So you have more dense material.
right. So the calorimeters, well, the inner tracker that we build out of silicon, you specifically want the particles to be able to move all the way through that. But then in the next layers, you try to stop the particles. So that's what the calorimeters do. And for example, the electromagnetic calorimeters are these crystals that are grown. There's 70-odd thousand crystals that were grown just for the electromagnetic calorimeter. The hadronic calorimeter has special layers of brass.
Yeah. And steel, and these are very, very dense. The point here is you want to slow down the particles, and they are basically stopping these particles. Some particles will escape through after the magnet, but we can discuss that in a minute. Maybe we can go back to Derek. He's showing us a really cool view.
Awesome.
Yeah, so we're up, I would say on the top, but we're not actually on the top of the detector because the detector's over there. But you see there is actually stairs that go up to the top because sometimes you need access up there. But basically, I hope this gives a better sense of the scale of the room also. We had to go up, what, 1, 2, 3 flights to get up here. And it really gives you a little bit of unease because we're quite high up, but I'm not that afraid of heights, so it's okay. The CMS detector, as we said, is all put together right now. So we're ready to do our experiment. And it is kind of this giant block, this giant thing. But as Claire and Andreas is trying to convey, there's many different layers inside of this thing that we're looking at. And each one of those layers has a very specific job, whether it's the innermost layers to get the initial trajectories, or the other layers they talked about, which catch or stop certain particles and try to measure their energy. We can't do it all though. Some particles escape, and it's actually in our name, but the particle that escapes the most of our, besides maybe neutrinos, but we'll ignore that, is the muons. So muons are like this heavy electron. The point is they're an exotic particle, little higher energy that we would like to study in our experiments. And they make it all the way from the innermost part to the edge of our detector and even escape the edges. And it's in our name, compact muon solenoid. We really like muons.
We do. We really like muons. Muons are my favorite particle. What's your favorite particle? Everyone should have a favorite particle.
Derek, you got a favorite?
Well, on CERN, or on one of the web pages of CERN, there's a particle quiz. Maybe we can link it later, but you can find out what particle you are. I took it, it said I'm a W boson, and I think I agree. I really like the W bosons because said the bosons are the party particles. So I like that.
What's your favorite?
I don't know. I would say maybe the tau. The tau is interesting. It's still a lepton, but it can also decay hadronically.
Yes.
Yeah, it's difficult. It's challenging. It's interesting. So yeah,
Saying I'm the top.
You're the top.
You're the top.
Right?
You're the boss, right?
That's definitely the boss.
So we got a couple of questions maybe we could answer along the way. So since you mentioned muons, there's one question about the alignment of the detector. So we have a question from Gigi. Yeah, Guru. So it's about whether, for example, if there's an earthquake and the detector is shaken, could that knock it out of alignment? And so we don't have many earthquakes in the Geneva area here, but I did mention that our detector is modular. And what I didn't say is that what I kind of alluded to is that we have periods of maintenance at the end of every year. And most of the time we open up our detector in some way. So that means we move the slices around, and that it certainly changes the alignment of the detector. And so one of the ways that we can basically understand the alignment of the detector is we use muons that are produced from cosmic rays. They scatter in the atmosphere, they're produced in the atmosphere, and they go through the Earth, and we can look at these muons that are produced from cosmic rays in our detector, and we use that information to understand the alignment of all the components in our detector.
And one of the reasons why this particular region was chosen for to build the LHC and you know, hopefully the future circular collider in the future and all that is because it is such a geologically stable region. But one of the things that you might be interested to know is that the LHC beam can or is affected by the phases of the moon, because the tunnel goes through rock, and we have Lake Geneva nearby. And as the phases of the moon changes, we have basically tides on Lake Geneva, and it's not really noticeable to us, but it does put pressure on the surrounding rock, which can affect it. It adjusts the LHC beam by a few millimeters, centimeter each year, each month.
Don't know.
A little bit.
Bit.
It's definitely noticeable.
But
Exactly.
it's noticeable in the operation of the beam. And I know Claire has also seen this. We have from earthquakes that have occurred, this also can be seen in the trajectory of the beams.
Yeah, basically the protons keep going straight, and the ground shakes around the protons, around the beam. So what we see, or what the people see in the CERN control center is, you see what it looks like is the proton beam going up and up and down, up and down, and up and down.
Yeah.
But actually, it's because the protons just keep on going straight because inertia, and the ground is you know, oscillating around them. It's very cool.
And all the
So-
equipment is designed for Richter scale 5 earthquakes that happen something like one in every 1,000 years.
Yeah. So we can withstand 5 on the Richter scale.
That's absolutely necessary. Otherwise, the cavern would tumble down. This we anyway want to avoid of. But
So-
you are absolutely right. So there is one thing that we are designed for quite high earthquakes. The second thing is that if it happens, we would realign.
Yeah. So
Okay.
that is
Hello.
thankfully one thing that we do not have to worry too much about.
Yeah. So let's go back to Derek. I think
So-
he's
I just wanted to, before we moved on, show you this giant orange absorber. We talked about it earlier, but you may be wondering where the proton beam is or where it's coming from. And it's actually inside of this orange block is where that beam pipe is. So of course we cannot see it, but it is totally covered and encapsulated by this giant orange absorber. And so you would, if it were pulled apart, like when we're doing maintenance, you would see the beam pipe going in directly into the side of CMS, and then our proton beam collides in the dead center. And then that is, of course, where we do the experiment in the middle of our detector. But I just wanted to point that out in case there's anybody wondering, where is the beam coming from? It's originating in here and then going into the other, well, the middle of CMS. And on the other side, we have the same setup. So we're now going to move on to a lower part and check out the field again.
So
Maybe
while
there's
you're
questions
climbing
or-
around
Yeah?
there, you know, there's been a few people who have noted how huge this thing is, and you know, it's not just huge in size. There are millions of components, and it really took thousands of people from hundreds of countries a number of years to design and build it. I think the first designs started 30 years ago, right?
yeah. In fact, our collaboration celebrated its 30 years 2 years ago. I think 2 years ago.
1993.
1993. So it's 33rd birthday this year.
Yeah.
So we started building in the early 2000s. That's when they started digging the ground out to put it. But already by that point, things had been in, you know, under design, prototyping, and already a lot of the components had started to be built.
Yeah, I think one of the most interesting systems that you mentioned before is the crystal calorimeter. So we have these crystals that are basically the main component in our electromagnetic calorimeter. They are crystals, but they have to be grown in a lab, and they are more than 80, they're, I think, about 85% lead. So these are extremely heavy, mostly lead crystals, and they're scintillators. That means when a particle hits it, it will produce light.
They're see-through, by the way. They're
Yeah.
mostly lead, but they are completely see-through. In fact, if you looked at it next to a block of glass that was in the same shape, you would not be able to tell the difference
Exactly.
until you picked them up.
And so each of these crystals, actually, Claire already mentioned that we needed to produce about more than 75,000 of them. But it turns out each of them takes about 2 days to grow. And so given all of the constraints that we had, it means that it took about 10 years to grow all the crystals just for this system, just one of the systems that make up all of CMS. And that also gives you an idea, a sense of the lifetime of CMS. We started the collaboration 30 years ago already, and we're expecting to continue running the LHC until 2040 something, 2040 at least. And that also should, it's a reminder for ourselves to talk about the upgrade at some point. Yeah.
Yeah,
So-
you know. Oh, yes, Derek.
I don't know if sometimes tell me if my mic isn't quite working. Last time we
Okay.
did this,
Yeah.
being this close to the field, I think affected the mic. And for those at home, speakers and microphones work with magnets. So if you're near a very strong field, it could affect it. But we're going to walk along the side of the detector, and you can then again see some of these slices, how it's put together. And we'll look at some of the electronics. You might also see some cooling that's involved. But yeah, keep your eyes peeled. There's just a lot of stuff going on through all these different layers.
While we're there, actually, we can see all of these wires. And Mustafa wants to know if we get induced current in the wires and if this causes noise.
So there's a hint to something that Derek said before. He mentioned static fields, right? So the magnetic field is static. This is, I mentioned already on Monday, we had to ramp the current, right? So we added current to the magnet, and that increases the magnetic field. During that process, you may have induced currents when the magnetic field is changing, but you don't have these currents when you have a static field. However, there are a few things to consider. So one of the things that we have, you can see a lot of wires, and a lot of these could be high voltage and low voltage, but we also, for the most part, read out our detector. And in fact, we communicate with our detector using fiber optic cables. And a big part of the reason is you can think, and it's also a consideration, latency is a consideration, but another big part of the reason is we have lots of cables, extremely long cables. Some of them go all the way up to the surface, so they could be more than 100 meters. And so you don't want to pick up interference from copper cables. So that's, you really need, you require these fiber optics in order to reduce that interference.
So we've had a lot of questions about how do we power this sort of thing, especially Divinity wants to know how much power is used and where does this energy come from. So first of all, to run the Large Hadron Collider, that's the accelerator that is accelerating the protons and smashing them together, as well as the 4 large experiments, it uses about 180 megawatts when everything is up and running. In fact, there's a like a dial in the CERN control center where they constantly monitor how much power is being used. And this comes largely from the French power grid, which
exclusively.
Or basically, apart from a couple of times a year when the French do maintenance and then we switch over to the Swiss grid or something. But yeah. But as you know, the French power is mostly nuclear as well. So we basically are running as much as possible on I wouldn't say renewable, but at least it's the best.
According to the European Union's classification, it's renewable.
It's renewable, yeah.
But extremely little, carbon, fossil fuels.
Exactly.
Exactly.
It's carbon free.
And then a lot of other CERN. So CERN also is trying to maximize its sustainability. Like one of the things that is being done at the moment is water that is used for cooling in parts of the experiment is used to pump through some of the neighboring villages for heating houses.
Yeah, so that's being set up, and it actually is going to the village where I live, so I'm very happy about that. And yeah, there's new infrastructure that is using. So there's all sorts of different needs for the power. So sometimes you have cryogenics that need to be kept at certain temperatures, but sometimes you have some non-superconducting magnets, and these will generate heat. These are electromagnets. And so the water that's required to operate these, sorry, the water that's required to cool these magnets is then used as a heat source. Okay, so
Derek, try to use the spanner instead.
Just don't thwack it on something as
We're
you
taking-
walk past.
We're taking the chain for a walk, and watching the field. And yeah, it's hard to keep it away from anything it might stick to, but. So we're just about back to where we started. We just have to walk around the edge here. But yeah, I think we're going to, from down here, we'd love to take any more questions. If there's anything that people would like us to show actually up close, or to
I
go
have
somewhere else in the room.
one thing
Yeah.
that could be interesting. So you have the blue winch system that is used to move the slices, and it's on your left here.
Yes.
So this could be
So right
interesting
here.
to look at. Yeah, so I mentioned before that our detector is modular and we can move the slices. In order to do this, we use this winch system, which has this very sturdy metal cables. And this is used to pull on the slices, but again, these slices are 300 to 2,000 tons, so extremely heavy. So in order for us to be able to do this, to move the slices, we have another system, and these are the orange feet on each of the slices. These are air pads that we use, and the system here is we use compressed air. This works a little bit like a hovercraft, so this will lift the slice just a few millimeters. It requires a lot of air pressure to do this, but then that allows us to reduce friction enough to move the slices.
And you can actually see here on the ground, there's some wear. So even with the system and the air pressure, there is still some, what would you say? Scratches, but there's still some, quite a lot of weight on the ground. And you
Yeah.
can see it go all the way.
2,000
Along here.
tons is quite a lot to lift. Another thing, if you're interested in sort of like mechanics of moving heavy things, another thing to think about is actually our entire detector is tilted at a slight angle, just a couple of degrees, and that's because the entire LHC is tilted at a slight angle, and we have to be,
I think,
perpendicular.
1.4 degrees.
Yeah.
So it's very, very a small amount, but it's noticeable.
Yeah, especially when you're trying to pull something that's 2,000 tons.
Exactly, because
And also the number of steps.
Yeah, you have to move up. Yeah, so just the mechanics and the logistics of doing something, just to pull a slice out so you can fix something, right?
So since we're under the forward shielding, there was one question about what it's made of, and I'm fairly certain it's steel and concrete. Does it have concrete as well? So reinforced concrete is the short answer. But I should mention that we have, what you see is mostly the new forward shielding. We have the original shielding just under there. And this new shielding was added in anticipation for the upgrade, which I think we should really discuss before we're out of time.
Yes. But before we go there, let's talk a little bit about the physics. So one of the things that the CMS experiment is famous for is the discovery of the Higgs boson with the ATLAS experiment. So ATLAS and CMS are kind of brother sister kind of competition experiments on either side of the LHC ring.
Yeah, I think a sibling rivalry is a good
Yeah.
way to describe it.
And in 2012, we announced the discovery of the Higgs boson, which some of you may know as the God particle, although the physicists don't really like to call it that.
Yeah, even the person who came up with the name didn't really like.
Well, he didn't come up with the name the God
yeah.
particle. He called it the goddamn particle.
Yeah.
And then his publisher decided to change it.
Yes.
So.
And there's actually a bit more behind that story, and maybe I could use this as a promotion for the CERN podcast. So it's Morning Coffee with CERN, I think. So they have one episode where they describe this story in a bit more detail. So I encourage you to check it out.
So how do we discover a Higgs boson? So, it was quite a long story. I mean, the idea that this particle existed was actually proposed back in 1964. And it took until 2012 for us to actually be able to build a machine that could create it for us to discover it. And what you see on the screen here is a picture of the plot or the physics results where we proved conclusively that this thing existed. And what happens is a Higgs boson, we can create a Higgs boson, we can create them by smashing together protons. In fact, it's pretty easy. I think 1 in every 10 billion collisions creates a Higgs boson.
Well, it's easy if you have an LHC.
It's easy if you have an LHC. So once we had the LHC.
I mean, it also took a long time to discover it because you needed a machine that was capable of producing collisions with this amount of energy to begin with, and as often as we do.
Right. But so, okay, once we had that, and once we were smashing the protons together, we were able to create these Higgs bosons. Now, the thing about a Higgs is that it does not live for a very long, it does not live for very long at all. It lives for a tiny, tiny fraction of a second. And then it disintegrates into other particles, like I think in this case, into 2 photons. Yeah. So what you have to do is you're not looking through your data for signals from a Higgs boson. You're looking for signals from 2 photons. And then you have to match those 2 photons up, see if they came from about the same place in this event, and then you work out if they did come from the same event, and if that was a particle, what would the mass of that particle be? And so what you see in this plot, it's basically just, this is the type of plot that you see a lot from physics, but it's not very difficult at all. What you see on the x-axis, that's the mass of this 2 photons. So
which is basically the same thing as saying the energy, the total energy of these 2 photons.
Yeah. And basically on the y-axis, it's just counting. So it's how many of these did I see at 100 GeV, 110, 15, 20, 25, etc.
Yeah. So how many events, as we call them, with this amount of energy with exactly 2 photons that we see in this data.
Exactly.
And in fact, maybe I could go a bit further. So what you see, the black dots, I'm talking especially about the topmost part of the plot, you see the black dots, and that's the actual data. But then you have the sort of naive prediction that the Higgs doesn't exist at all, and that would be just a slowly, monotonically decreasing slope.
I think that's like a dashed line or something. Or
exactly, it's a bit hard to tell, but the point is that you can see that these events from the Higgs are an excess from what we call the background, meaning that if the Higgs was not there, we would not see all these extra events. And that's how we were able to indirectly discover the Higgs. But of course, this is a rigorous scientific result with rigorous statistical analysis of the data.
Yeah, that smooth curve is basically just what you get from random stuff that produces 2 photons. And then if you have a particle at a particular mass or energy, then you would get more events than the random. And that's why you see this tiny little bump. So whenever you look at like a physics plot like this, if you see a bump usually means a particle.
So there's of course a lot more that we could discuss. This is just the tip of the iceberg. since 2012, we have investigated the Higgs very comprehensively, and we know quite a bit more about the Higgs now. So we can tell you that it looks a lot like a standard model Higgs, but they're still open questions. So it's the most recently discovered particle. So it is definitely where a lot of the research activity is focused on at the moment. And we can, of course, say that we hope to use the Higgs boson as a tool to understand potentially other parts of physics that we don't really understand yet.
There was a quick comment about the error bars in the lower plot. So yes, this is fine. What you really want to do is you're comparing basically the size of that bump to the height of the error bars. So you're seeing that the bump is significantly bigger than the error bars. The other thing to notice is this was with the very first set of data, and we've continued to collect more data and make this plot again. And as time has gone on and we've got more data, those error bars have shrunk and the size of the bump has got bigger.
Yeah.
So that means it's real.
This was run 1, which was like 4 inverse femtobarn. I don't quite remember. So we have about
500 now.
100. Yeah, we have 500 now. So we have 100 times more data.
Yep.
So yes.
So Anders and Derek, where do we go from here in terms of, because I know you're dying to talk about the upgrade. So what can we do beyond the Higgs? What are we hoping for beyond the Higgs? And why do we need to upgrade our experiment to do it?
So if I could say some things, I mean, there's two main ways you can push our understanding of the standard model and particle physics forward. And so the main ways I'm talking about is with more energy. If you collide at a higher energy, you can produce more exotic particles that we may or may not, know about or think exist. Of course, we theorize them and then try to find them. So you can do higher energy collisions, but the other thing you can do is you can actually do more collisions, which is the kind of the statistics side. If you get a ton of data, you can do very, very precise measurements. And so you were talking about the error bars on some of those plots. You can really get the error bars very, very tiny if you have a lot of data. And so this is where we're going in the short term, meaning in the next few years with CMS and the other experiments at CERN. We are upgrading the Large Hadron Collider to do more proton-proton collisions so that we get much more data. But also we need to upgrade our detector so that it can handle more proton-proton collisions. It needs to be able to read out quicker, or you could say more. It needs to be able to read out significantly more because we're going to be increasing the collisions by how much? We do about 60, pile up 60.
Every 25
million.
nanoseconds.
Yeah.
Every 25 nanoseconds, we have roughly 60 collisions. We try that in a bunch crossing. But after this upgrade, we're going to have what, about 200?
Yeah.
Every
25
bunch
nanoseconds.
crossing?
Mm-hmm.
Yes. So we're going to have significantly more collisions. And you can imagine with a camera, our detector is kind of like a camera. But think of your camera. If you were to just turn up the lights, your camera sensor might be overwhelmed by how much light there is to look at. So if we do more collisions, we need to upgrade our camera, our detector, to be able to actually read out and observe more of those collisions without being overwhelmed by the sheer increase of collisions. So that's what we're doing in the next 6 years. We're going to shut down and be upgrading quite a lot of our detector here.
And what part of this are you working on? Yes, for those of you asking, we're all three of us are physicists. What are you working on in terms of the upgrade?
So Claire and I work on some similar things, but I think the three of us, we work on some different parts so we can actually elaborate on each. But I work on the innermost part, which is the pixels. So they are not unlike, they're very similar to the pixels in your camera, but they are for observing particles that pass through them, high energy, charged, electrically charged particles. And so these pixels totally need replaced because the ones in here right now are very radiation damaged, but they also need to be a bit smaller and they need to have some upgraded capabilities, to handle this increase of collisions. So I'm working on the innermost part. I'm very excited to take things apart and install them. You can go ahead and share what you guys are working on.
You want to talk?
Sure. So I specialize, let's say, in the measurement of luminosity, and we have multiple instruments that we use to measure luminosity. So I'm working on the upgrades. But yeah, that's a big part of the measurements is knowing how much data you have. So when we said every bunch crossing, every time we have protons crossing, you have on the order of 160 billion protons that get close to 160 billion protons. And as we said, in current conditions, we can get about 60 of them to interact. And we want to push this number up to 200 or more. And that requires upgrading our detector, but also from the LHC, they need to have incredibly significant upgrades. So one way you accomplish this basically is you need to focus the protons to occupy a smaller space, if you will. And you do that with magnets, do that with superconducting magnets. And we actually need to develop magnets with a different type of superconducting material in order to get to the magnetic fields required for this. So that just gives you an idea of the level of complexity that's required to accomplish this upgrade. And then from the side of CMS, we are essentially replacing our entire inner detector. That's basically completely new from scratch. And also what we call the end caps. So that's also getting completely replaced. There's many other upgrades, but those projects alone, each of them, you can probably consider it on the order of a space telescope in terms of complexity. Building one of these projects are just incredibly complicated. And this is now where most of the attention is going, most of the effort is going, is to produce these detectors and install them and commission them in the next few years.
Awesome. So I'm going to not talk about what I'm working on, but I'm going to talk about the why we're doing this, because Cyber something asked us a bit of a question on can we discover new things without necessarily increasing the energy? And I think it's important to say this upgrade that we're talking about does not have an energy increase.
Yeah, it's extremely non-trivial to increase the energy, because what you need is to also replace the dipole magnets, and that will be simply too expensive. And we're not there in terms of technology.
No, we're hoping in the future to build a 100-kilometer long accelerator, but we're not there yet. So what can we do now, and why? And is it important? So if we take everything that we know of in the universe, all of this stuff that makes up you and me and everything, this sums up to a total of 5% of the universe. And we know that there is something called dark matter out there, but we have no idea what it is. In fact, there's 5 times more dark matter than normal everyday stuff. And black holes, neutron stars, all of this, that's all normal. That's all part of the normal stuff. So dark matter is none of that. We have no idea what it is. But we do know that it has mass. And now the key thing here is that because dark matter does not interact with us, with the normal forces that we have, like with light, with the strong, weak nuclear force, it's very difficult to catch or detect dark matter. But because dark matter has mass, that should mean that it interacts with the Higgs boson somehow, because the Higgs field, the Higgs talks to everything that has mass.
Yeah, it's the mechanism by which fundamental particles acquire mass.
Right.
Or at least that's our current understanding.
Yeah.
So it by definition, if it has mass, it participates in the Higgs mechanism, so it can talk to the Higgs.
So one of the things that we've actually been doing, the Higgs, as you saw in that plot from earlier, the Higgs can disintegrate into photons, but it can also disintegrate into other things, W bosons like Derek. It can disintegrate into Z bosons, electrons, muons, all sorts of things. And over the past 13 years, 14 years, since the discovery of the Higgs, we have been measuring the percentages of how much it turns into photons and how much it turns into each of these other things. And so you can imagine a cake. Imagine you taking a cake, and that cake is all like the ways that the Higgs boson can disintegrate. And you slice up the cake, so you've got a slice, and that's the percentage of decaying into B quarks, and you've got another slice for Derek W bosons, et cetera, et cetera, et cetera. Now, one of the things that could happen is that the Higgs boson could disintegrate into dark matter. Now, we might not be able to catch the dark matter in our detector, but if we can measure these slices of cake to a high enough precision, then we would maybe be able to start seeing a tiny wedge that is the Higgs turning into dark matter. And up until this point, you can think of our knife that we've been using to cut the cake as a very thick, blunt knife. So we haven't been able to cut with close enough precision to finally determine the exact percentages here. So there still is, if we collect more data, even at the same energy, we may be able to start seeing a very, very tiny slice, because more data is essentially giving us a much, much more sharp, precise knife to cut.
That's a really, really nice analogy.
Also cake.
And also it's cake. So who doesn't like cake?
Actually, that's called indirect search.
Exactly. It's an indirect search. And just to add a little bit, so we can actually predict how often the Higgs will decay into this or that. And that's what we do. We compare the Higgs that we expect given the expectation that we have, the description, the physics that we have. We can predict this, and then we go out and measure it. But when you're talking about the most rare type of interactions, the most rare decays, then it becomes a lot more difficult, because then that's where we need the most data, right? That's where a fine knife will make a difference. So it's also, we're focusing more on the experimental side, but there's also progress to be made on the theory side. But precision is key, right? And that's one of the sort of the drive forward is to improve precision. Yeah.
To also just provide one final analogy, it's, how closely can you look at something? So with this precision, we're just looking even closer than before. And some of these things that we want to study, like the Higgs and the dark matter and everything, may require you to look closer than humans have ever looked at anything in nature before. So it's we're really pushing the boundaries here. We're not just having fun all the time with magnets.
But we are still having fun.
Well, yeah, it's true. We are.
But yeah, there's no guarantee, like there's no way of saying, oh, okay, if you do this, you will discover dark matter. If you build an accelerator with this much more energy, you will discover something. We don't know that. But you know what? That's fine. That's the equivalent of.
It's really exploration.
Exactly. Like it's setting off on a boat, or setting off, in a spaceship, going into the sky and seeing what we come across.
Well, this is science. A null result, or the result proving it doesn't exist, is still a result. And this has a lot of historical, implications. When we were trying to understand light, we used to think maybe since it travels as a wave, it has some medium. And then they did experiments and they found, well, actually, no, there doesn't seem like there is a medium. And then that gave us the direction to try something else. So even if we look for dark matter and don't find it, it's an indication, it's still a result, but an indication that maybe we should try something else. Maybe we should look somewhere else.
It just, we still learn something, right? We learn what dark matter isn't, which is also quite important. So we unfortunately need to start wrapping up. You guys have kept us really busy with all of your amazing questions, and I'm really sorry if we weren't able to get to your question. Brief we could do like a brief thing. Is machine learning useful? Very, very useful, becoming more important. We're using machine learning to get more sophisticated analysis techniques.
But it's also worth pointing out that we were using machine learning before it was called machine learning. So yeah, so let's say yes, very much. There's a question about civil engineering. There's too much to say. There's a lot of contributions from civil engineering. There continues to be. Still at the CMS site, we have some civil engineering that's dropping up for the upgrade, but we have civil engineers here at CERN.
And hopefully one day we're going to dig a 100-kilometer long tunnel.
Yes. And there was a funny question about Godzilla and something about the radiation. So in these collisions, we do produce ionizing radiation, so it's a consideration, but that's something that we basically have to deal with. This is partly why the inner detectors deteriorate, and it's also why there's safety implementations, why the access is extremely important, why we have dosimeters and so on. So this is certainly something we deal with.
There's a question on antimatter. Very normal. We produce it all the time. In fact, when I say the Higgs turns into electrons, it's, you know, electrons and anti-electrons because it has to balance. So yeah, antimatter is pretty boring, actually. It's just one of the useful things.
It's something
when you eat a
well.
Sure, and when you eat a banana, there are isotopes of potassium that produce positrons, anti-electrons. So it's all throughout nature. Antimatter is part of what we live in, the world. Yeah.
Okay, so and then last question, there's a question about supercomputers to analyze the data. I'm sure there are some sort of supercomputers, but what we use is computer clusters, and we also make heavy use of distributed computing. And we have done so for a long time. This is another area where we have innovated a lot. I think maybe to wrap up, I would say that there's many examples where the kind of physics that we do will drive innovation in areas that end up affecting everyone on Earth, right? So the World Wide Web is the obvious example, but I also mentioned superconductivity. So material science for superconductor, that's also where contributions have been made. So yes, Claire, I don't know if there's any other last question we can answer, but maybe we're out of time.
I think we're getting told they're gonna grab us with a hook soon. So to everyone, thank you so much for joining us. I hope you enjoyed. Special thank you to Derek Underground over there for showing all the detector.
I mean, absolutely my pleasure. This is so fun.
You look like you're having so much fun.
I think we lost him quite long ago.
I'll be surprised if he comes back up again.
Please don't forget anything down there.
Yeah.
Yes.
So Derek, thank you to my co-host Andres,
Thanks
and
to you.
it's a pleasure. And thank you
Thanks
to our
to our
technical
technical
team,
team, yes.
Zoltan and Naomi.
Thank you to Naomi.
Yep, thank you, Naomi.
Team.
Oh yeah.
And to everybody in the control room for keeping the detector running. And thank you most especially to those of you who joined us today and who asked your fantastic questions.
Great.
So yeah, hope to see you again too. Bye everyone.
See you.
Thanks.
Ciao, ciao, bye.